Okay, today we are going to cover 3.6. Now, I needed to talk to you a little bit about the reservations for the meeting with me for bonus. So I'll just tell you kind of in short how it was supposed to work. I was going to go into the calendar in Canvas and then allow you to reserve time slots, but I have to actually manually put each of those time slots in, all 10-minute time slots for each day for the entire term. It's a pain in the butt. So what I'm going to do instead is on Tuesday, I'm going to have like a calendar with time slots, and you're just going to put your name on what time. So between now and Tuesday, try and think about a day and a time you'd want to come in if you're interested in that bonus, okay? I know some of you have already reserved for next week, and those are okay if you reserve for next week, except on Monday. If you reserve one for Monday, can't do it, campus is closed. I forgot about that when I put them up there. So, okay, Monday's a holiday. So next week, there will be a sign-in sheet for coming in for the 10-minute meet me and all that stuff. Questions on that? Okay, so we are going to cover 3.6 today. The good news is that for 3.6, there's not a lot that's visual, so I won't need my computer. I was going to show you something cool, but technology, right? So instead, we'll just have to do it old school style, where I'll just write on the board. The lecture notes for this section is only 1 page long. So if you found my notes on Canvas, I take that back. Yeah, it's 1 page. One? Maybe a little bit more. I take that completely back. It's 4 pages long. So I thought I might motivate the whole idea of this section, or at least one of the results of this section, with an example, all right? With something tangible that you can see. So let's see how I can do this here. Oops. I have all these straps in the back of my truck, and I happen to grab like the dirtiest, nastiest one I had. All the other ones are like bright orange, and this one's like, can't even see it. Let's see if I can hook this up here. I might need a volunteer, but let's see. That'll hold. Okay, so if I take a wire or a rope and I were to suspend it between two points, all right, like this, I'm going to get this shape, right? What shape does that look like to you? Looks like a parabola, doesn't it? So we might be able to model this shape with some function ax squared plus bx plus c. But that's kind of a question. We don't quite know if we could do that, right? It looks like a parabola. You could also argue that perhaps it's some sort of sine curve. Something that's a d at the end, okay? Maybe, doesn't it look like part of a sine, like maybe the bottom portion of a sine or a cosine curve? So again, it's a question, is that possible to get it with this, or maybe there's something else? So when you look at the parabolas like this, by changing a, b, and c, it changes the shape, right? You can kind of make the parabola spread out. You can move it up and down, left and right, right? But with that hanging wire, let me put that wire here again, or that rope. With that hanging rope, it is actually not possible, it's impossible, to change your A, B, and C in just a way so that every single point on that hanging wire would be on the parabola. It's just the way that parabolas are shaped. You can control the shape, but you don't have complete control as to how fast they turn. So there's no way you could do it, all right? You just have to trust me on that it's not possible. And then also, there's no way to do it with a sine curve. So as mathematicians and physicists, we're trying to figure out what function actually does this. It turned out that it required a different classification of function called the hyperbolic trigonometric functions. All right? And that's what today is about. Okay? So I'm actually going to show you the function that describes the curve that is formed when you hang any wire or rope between 2 points. All right? These are called catenaries, but we'll talk about that later. The difference between a parabola and this thing, which is called a hyperbolic trig function, is that if you were to try and model that with a parabola, you might be able to get some points to land exactly on that curve, but if some of them do land, other ones are going to miss. It's just not possible for a parabola to curve exactly the way a hanging rope curves. Does that kind of make sense? Sure? Okay. All right, so before I begin with the hyperbolic trig functions, let's recall, and that means going back to what we already know. All right, let's recall some things about pre-cal. We have from pre-cal sine x, cosine x, tangent x, cosecant x, secant x, and cotangent x, right? So when you're in pre-cal, we introduce the 6 trigonometric functions, right? And do you remember how we actually defined sine? Like, what was the definition of sine? How was the topic introduced to you?
Y intercept.
What's that?
Y intercept.
If you were trying to explain to somebody what sine of something was, what are you going to reference? Like, what is it that you... Opposite over hypotenuse, remember sine? Opposite. So, but that was all based on a right triangle, right? So if I draw a right triangle, and we call this, well, we could replace these with thetas, right? But whatever the angle is here, theta, we call this side maybe y and this side x, then that's the way we developed sine, cosine, tangent, right? Oh, that's all I want you to remember is that all those 6 trig functions were created using the right triangle, right? Okay, and then after you did that, you talked about the inverses of these, right? So later on you say, all right, each one of these has an inverse, and that's what we did last class, right?
Yeah.
We talked about the derivatives of those, blah, blah, blah. So in pre-cal, you have 6 functions and their inverses, right? And then in calculus 1, you realize that there are 6 derivatives of these, right? Each one of these has a derivative. And then last class, we talked about the derivatives of these. So now what today is about, I guess if we're counting, how many functions do we actually have here? We have 6 plus their 6 derivatives, right? That's 12. And then we have 6 inverse trig functions and their derivatives, so that's another 12. So we have 24 functions right now, don't we? Okay, today we introduce another 24. All at one time, all right? In one day, okay? So now we have what are called the hyperbolic trig functions. And I'm going to put them up here. I'm going to list them out, and then we'll talk about, what they are. All right, so we have what's called the hyperbolic sine function, and the way you write it is sine with an h and then x. So the only difference between the sine function and the hyperbolic sine function is that h right there in front of the x. Then cosine hyperbolic x, tangent hyperbolic x, cosecant hyperbolic x, secant hyperbolic x, and cotangent hyperbolic x. Now, what do you think each of these 6 hyperbolic trig functions have? Derivatives, and they also have inverses, and each of those inverses has derivatives. All right? But before I get into those other functions, what is the definition of hyperbolic sine? And that's why I asked you about the definition of the sine. You said, okay, that came off a right triangle, right? So how are we going to define this new function called the hyperbolic sine function? And here it is. Here's the definition of the hyperbolic sine function. Hyperbolic sine of x is defined to be. Now, if you ever see a colon in front of an equal sign, that means that we are defining something. All right? We are telling you, look, when you see this, it is defined to be the following. E to the x, what? Minus e to the negative x, over 2. What? Okay, this came off of a right triangle, right? That's how we define it, opposite over hypotenuse, blah, blah, blah. These new hyperbolic functions actually don't involve triangles. They involve some combination of exponential functions. See this? If you'd like, you could rewrite this way. So all I did was pop that 2 out of the bottom, right? Brought it out as a 1/2. You will see me write it both ways, all right? Now, I won't usually write it this way, but this helps us kind of think about what's happening here. Do you know what this function right there looks like? Do you know what that function looks like? E to the x? You should, right? It's like, it does something like that. Exponential, whoosh, like this. And then do you know what e to the negative x looks like? It's actually a reflection of that one. It goes like that instead. So if we subtract the two, it's like, this is the same as like adding the opposite. So somehow we're combining these two functions together to create a new function, and that new function is the hyperbolic sine function. All right? Now the graph of these, when I get my computer up and running, I'll show you the graphs, but they're in your book too. They show the graphs of these. And we're not going to spend 3 weeks graphing hyperbolic sine functions and cosine functions like we did in pre-cal. Okay, we're just not going to invest the time into that, and you're not going to be tested on that, all right? But just know that they have graphs, all right? That's the definition of sine hyperbolic. Now, what's the definition of cosine hyperbolic? Well, okay, so it's going to turn out to be really close to this. It's e to the x. Yeah, the only difference is this is a plus. Everything else is the same. See? Minus, plus. That's it. That's all that changes. And so if you factor out that 1/2, you get this. And then what would tangent hyperbolic of x be? So that thing divided by this thing, right? So good news, all right? Tangent hyperbolic of x is kind of like the same as tangent was over here in pre-cal. It's sine over cosine. It's sine hyperbolic x divided by cosine hyperbolic x. So yes, these are all going to be reciprocal functions. So like cosecant hyperbolic is 1 over sine hyperbolic, secant hyperbolic is 1 over cosine hyperbolic, and cotangent hyperbolic is just tangent flipped over. Make sense? Okay. Now, if we had to do this mechanically, wouldn't this be 1/2 e to the x minus e to the negative x over 1/2 e to the x plus e to the negative x? Right, that's what sine and cosine are. And if we cancel the halves, which we're allowed to do, then we just get e to the x minus, oh, whoa, I'm probably way off camera here. I've got e to the x minus e to the negative x over e to the x plus e to the negative x. So I have a question. Can I do anything with that? Like, is there any algebra? Like, can I cancel these? Please tell me no. No. Please tell me no. Right? Don't do any crazy algebra that's not allowed here, okay? Don't do anything that would break rules. That's pretty much all you can do. Now, there is this. Isn't e to the negative x 1 over e to the x? Right? Aren't both of these just 1 over e to the x? So sometimes when people have this expression, what they'll do is they will come in and multiply the top and bottom by e to the x. And what that has the effect of doing is clearing the fractions out. See that e to the x on the bottom? If you multiply this here and here, won't it clear it out on the second one? And let's just see what that would turn out to be. What would e to the x times e to the x be? E to the 2x, right? Same base, add exponents. So e to the 2x, and then I have minus, and then this times this? 1 over e to the 2x plus 1. So this is another way that you could define the hyperbolic tangent function. But this is the same as this, all right? You all right with that? All right, now, let's go back again and talk about pre-cal for a second. When we were introducing these 6 functions right here, do you remember you took a lot of time to discuss the properties of those functions, like some of the things that they have, characteristics? What were some of the major properties that you had from those trig functions? Can you think of like an identity or something that we use a lot that involves signs and
Plus cosine equals, or sine squared.
yeah, sine square. So you had like the Pythagorean identity. Let me see if I can remind you of these. This is probably like the holy grail of trigonometric identities. That one right there. But that wasn't the only one. There's a bunch of them, right? But that's probably one of the most important ones. And then we also had something, see if you remember this. That one and this one. Do you remember those properties? So this is the Pythagorean identity. I'm just going to put Pythag identity. Does anyone remember what that property is called? When a function, when you plug a negative into it, it's the same thing as plugging in the positive, but then changing the answer to negative?
Even and odd?
Even and odd. Okay, so which one is this one? Is this even or odd? Odd. Sine is an odd function. Remember that. Later on this semester, I think I'm going to blow your mind when I show you why it's actually called odd. All right? And then even. This is an even function. All right.
Is it because when you have it plotted and then you put a negative on the x, it stays the same or something like that?
Yeah, that's the geometric property of even and odd functions. An even function, when you graph an even function, like cosine is even. So if you were to take just what's over here to the right of x, or to the right of 0, and you were to just mirror it over the other side, it would be a mirror image of itself. That's what it means to be an even function, geometrically. And then to be an odd function, sine is odd. So here's sine. It's not a reflection like this. It's actually reflect here, which would give you this, right? But then reflect over the x-axis too. So like rotate it. And when you do that, you get the other half of the sine. So that's what it means. Even means reflect over the y, you land right on top of yourself. Odd means double reflect, reflect, and then you'll be right on top of yourself again. All right, so these properties we had, right? Okay, and there's a bunch more. I'm curious whether or not we have the same properties with the hyperbolic functions. I wonder if sine hyperbolic is odd. So this is a question. Is sine hyperbolic x odd? Well, we would need to make sure, we need to check, is sine hyperbolic of negative x equal to negative sine hyperbolic of x? Question mark. Is that true? Well, let's check it. We can check this, right? Because I've defined this. We've defined what sine hyperbolic is. It has e's and stuff in it, right? So this left side is 1/2 e to what? The formula is e to the x, right?
Yeah.
But I'm plugging in a negative x. So it's going to be e to the negative x. then minus e to the, in the formula it's negative, right? So negative x is actually going to give us a positive x, right? So the left side of this equation is 1/2 e to the negative x minus e to the positive x. Is that the same as, question mark, is that the same as this? So what is this? Well, that's, if these are equal, it's odd. If these are the same, it's odd. But what is this? I have a negative out front. And then what is the definition of sine hyperbolic? We've got 1/2 e to the x minus e to the negative x, right? That's what this is. See, I'm trying to compare. I'm looking like, is this equal to this? So is it? Are these the same? Yes, they are. Yes, if we distribute the negative through, right? Here, negative here, this negative goes away, this becomes negative, and this becomes positive. And even though they're backwards, right? These are backwards, the signs are correct. I have a negative in front of e to the x, and I have a positive in front of e to the negative x, and a 1/2 outside. So yes, indeed, they are the same. So the hyperbolic sine function is an odd function. Make sense or not? Sure? So far, what held up over here is holding up over here, so far. Let's try cosine. Is cosine odd? I mean, not, well, it's not odd. Is cosine even? Well, shall we check it? So what would we need? What do we need to check? If we want to know is cosine hyperbolic of x even? We need to check. So what do we need to check for this to be true? Is cosine hyperbolic of negative x equal to what? Just cosine hyperbolic of positive x. Are those the same? So if we plug negative in here, into the formula it was e to the x in the formula, so it's going to be e to the negative x, plus e to the negative x, so e to the positive x again. And the question is this equal to cosine hyperbolic x, which is so that's the definition of cosine hyperbolic x. This is what you get when you plug in negative x into cosine hyperbolic. You get this one. Are these the same? Yes. These are in the wrong order, right? But that doesn't matter. It's addition, right? So no issues. Just flip them over. They're the same. So check. Is it even? Yes. So again, things are looking very, very symmetric in a way. The things that happened here appear to be happening here, right? How about the Pythagorean identity? Is sine hyperbolic squared x plus cosine hyperbolic squared x equal to 1? Question mark. What does your gut tell you? What does your instinct tell you? Yeah, right? I mean, so far things have held up. How do we check it? We compute this, don't we? We compute it, and then we see if it equals 1. Yeah? Let's try it. So what does it mean to say hyperbolic sine squared? Well, that means I take the 1/2 e to the x minus e to the negative x. I take that whole thing, and I square it. And then I add to that the next piece, right? And I'm going to run out of room, so I need a little more space. I'm just going to move this over. So I have 1/2 e to the x minus e to the negative x, all of that squared, and I'm adding to that 1/2 e to the x, this time plus e to the negative x, that's cosine hyperbolic, then all of that squared. I'm hoping this turns out to be 1, right? So let's do this. If I square this whole thing, since there's multiplication here, I will square the half and then I'll square what's in the parentheses. So I'll get 1/4, and then I will have to square e to the x minus e to the negative x. I will have to take that and square that. Then over here I get, again, 1/4, and then I will have to take the e to the x plus the e to the negative x, and I will have to square that. Go with me? I'm checking, does this equal 1? Let's try and square this, all right? And this is just basic algebra, but it has some e's and stuff in it, so you start freaking out when you see it. But let's just do it over here. Okay, because some weird stuff happens. Okay, what about this first multiplication right there? What do you get? E to the 2x. Okay, next multiplication, this times this. Is it positive or negative? Negative, because I have positive and negative, so it's negative. What is e to the x times e to the negative x? 1. Because you're supposed to add the exponents, right? It's e to the positive x, and then I add this one, so I'm adding negative x. But that's just going to be 0 up here, and e to the 0 is 1. So that's just minus 1. Good. And then inside, again, add the exponents. You get e to the 0, you get minus 1 again. And finally, the last multiplication, positive or negative? Positive. E to the negative 2x, because you're adding the exponents. Negative x plus negative x is negative 2x. Is that all right? Okay, so that's what happens when I expand this one, right? Yes? And then this one over here, when I expand that, it's going to be the same computation over here, except I'm going to have pluses here, right? And the only difference is going to be that's going to make that a plus and that a plus, right? Okay, so I'm going to write that all down over here. So this is 1/4, and then when I expanded that, I got e to the 2x. Can I write minus 2 instead of minus 1, minus 1? Okay, plus e to the negative 2x. Then I have plus 1/4. And when I expand this, which I didn't show, it would be e to the x what? Or e to the 2x plus what? Plus 2 plus e to the minus 2x, right? That's what I would get. Does this equal 1? All right, how about we pass the 1/4 through everything for both of these? So 1/4 e to the 2x minus a half plus 1/4 e to the negative 2x plus 1/4 e to the 2x plus a half plus 1/4 e to the negative 2x. That's not 1, is it? Do you agree? This is not 1. I mean, what would we need for this to be 1? We'd need maybe like this one right here. These are like terms, aren't they? It'd be nice if these went away, like subtracted instead, right? Like, wouldn't it be great? I'm going to do this in blue, all right? Wouldn't it be outstanding, like, if this one right here was negative? Because then it would kill this one off, right? And then wouldn't it be great if this one right here was negative? Because then it would kill this one off, right? And wouldn't it be better if this was positive? Because then 1/2 plus 1/2 would be 1? So wouldn't it be great if this whole damn thing right here was negative? Like, change the signs of everything? What was that? This, right? Yeah. So wouldn't it be nice if this was a negative out here? Then it would work, right? Which means this won't work unless I make this negative. Do you follow that?
Yeah.
And that means that we don't have the Pythagorean identity. We have a version of it, but it's slightly different. Here's what it is. So this is what will appear in a book. This is the identity for hyperbolic. It's cosine hyperbolic squared x minus sine hyperbolic squared x equals 1. That's the identity you have with the hyperbolic trig functions. So it finally broke down. What happened in pre-cal, sine squared x plus cosine squared x was 1. That worked there, did not work here. However, we have a slight little tweak. If we just change that to minus, everything goes where we want it, and we get this. Do you follow me on that? I've never presented it that way. I usually just give the identity. I say, no, it's not, and here's the identity, and we prove it. I've never tried to like guess this and go backwards, so I hope that made sense. Okay. Now, you have a bunch of identities. In your notes, I list out some of the most important ones, but you just need to know, like on your formula sheets, right? You're allowed, on Canvas, I have the formula sheets that you're allowed to bring to the test. Those sheets include the hyperbolic trig functions and their definitions, so e to the x, blah, blah, you don't have to memorize all that. And it also has all the properties. So you just need to know they're there and refer to them when you need them, all right? Now, what about derivatives? What about the derivatives of the hyperbolic trig functions? So I'll start with this. We can get rid of that. So what have we done so far, just to kind of just make sure we're on the same page? Introduced the idea of hyperbolic trig functions, giving you what they're defined to be, and shown you a few properties, right? Now let's talk about the derivatives of these things. So derivatives all right, so how about this? Hyperbolic sine, what's the derivative? Well, you could just look on the formula sheet or you could just look in your book, but we should be able to figure it out, shouldn't we? So long as we can take a derivative of that thing. So that means what's the derivative of 1/2 e to the x minus e to the negative x, right? That's what this means. Take the derivative of that. What do you think the derivative is going to be? What does your instinct tell you? What are you hoping for? What are you hoping the derivative of hyperbolic sine is? I'm saying at the very end, what would you really like to have the answer be? Hyperbolic cosine, right? Wouldn't that be great? Because that would be just like in like the other trig functions. So derivative of sine is cosine. It would be nice if derivative of hyperbolic sine was hyperbolic cosine, right? Let's see if it is. So what about the 1/2 out here? It's attached to the function, right? So it just comes along. All right, now we take derivative of each of these terms separately. What's derivative of e to the x? Itself. Okay. Now, a little bit of chain rule here. Let's ignore the minus. So let's just write the minus down. All right, what's the derivative of e to the negative x? Negative e to the negative x. Where did the negative come from? The chain rule requires you take derivative of the exponent up there, and that gives you -1. So the derivative of e to the negative x is itself, but then times -1, which is where you get negative e to the negative x from. Yes? And that minus minus becomes plus. So you get 1/2 e to the x plus e to the negative x. And do you recognize that? That's cosine hyperbolic. Now, when you say this, I've heard it said many different ways. I've heard it said cosine hyperbolic, and I've heard, not many ways, 2 ways usually. Cosine hyperbolic of x, or I've heard hyperbolic cosine of x. You can like interchange which one comes first, hyperbolic cosine or cosine hyperbolic. All right, good. That's good news. Derivative of sine of hyperbolic is cosine hyperbolic. Great. So what about the derivative of cosine hyperbolic of x? What would it be great if it was equal to what? Negative sine, to be less for us to have to remember, right? It just follows what we've been doing. All right, let's try it. So we're taking 1/2 cosine hyperbolic is e to the x plus e to the negative x. And we're taking its derivative. That's what that little prime mark, right? That's what that means, derivative. All right, this is equal to, all right, the 1/2 just comes for the ride. What's the derivative of e to the x? Itself. Then I have plus the derivative of e to the negative x, which we just said was negative e to the negative x. So I'm just going to make that a minus now. What is that? That is exactly sine hyperbolic x. Crap. It's not negative sine hyperbolic x. It's sine hyperbolic x. Oh well, we just have to remember that. Okay, so back in pre-cal, derivative of sine is cosine. Derivative of cosine is negative sine, but in hyperbolics, derivative of hyperbolic sine is hyperbolic cosine, but derivative of hyperbolic cosine is just hyperbolic sine. Yes?
So just a quick question.
Yep.
Whenever you take the derivative, you don't mess with the 1/2 at all.
I do mess with it, but it's because of where it's positioned. We have this property from Cal 1 that says if you ever have a constant sitting in front of a function attached with multiplication, then the constant, my students would say, just comes for the ride. It just comes for the ride. Okay, so it's going to just sit out front, and then you take derivative of the function f. The only time the derivative of the constant becomes an issue is when it's by itself, and then the derivative of it is 0, right? But when it's just sitting out in front, like scaling the function, you just bring it with you. I'll give you an example, okay? This is a Cal 1 thing, but I'll still give it to you. All right, let's say that we have 2 times sine x, and I want to take the derivative. This is sine, not hyperbolic. You could, if you wanted to, although this would show a very, very low level of thinking, you could look at that as a product rule. You could, all right? And then you would say the derivative of this times this plus the derivative of this times this, right? So what's the derivative of 2? 0. Times sine x plus derivative of sine x, cosine x times 2. And what's your answer? 2 times cosine x, right? See, this, if you do a product rule here, if you do it, you're always going to kill that first piece off, always. So the other part of the product rule is always just going to be the derivative of this times that, right? So it's coming for the ride, and you're going to wind up just taking derivative of this. Yeah? So don't do a product rule. Just say, bring the 2 down, what's the derivative of sine x? That help? Okay. All right. So the derivative of sine, all right. Now, the remaining derivatives are in your book, but I'll put them up here because I don't have the notes to project. Normally I would project them. The derivative of tangent hyperbolic x. Do you remember what the derivative of tangent was in pre-cal? Or in Cal 1, sorry? Secant squared. You better remember that. You better have that hardwired. The derivative of tangent x is secant squared x. So it would be real nice if it was secant hyperbolic squared, right? It is. Good. So that one's kind of the same. We won't prove it, all right? It's going to take too long. Not that it's not possible. It's just I don't have time for it. I've shown you these two. You could do the rest yourself, all right? Do you remember what the derivative of cosecant, what cosecant was from Cal 1? No, derivative of cosecant. Negative cosecant, cotangent. That's it. Okay, so it would be nice if that's what this was. And it turns out that it is. Negative cosecant hyperbolic x cotangent hyperbolic x. Now, do you remember what the derivative of secant x was from Cal 1? Secant x times tangent x. And it would be nice if that's what it was, right? It's not. It's negative secant hyperbolic x tangent hyperbolic x. Close, but no cigar. Do you remember the derivative of cotangent of x in Cal 1? Negative cosecant squared, right? It would be really nice if this was negative cosecant hyperbolic squared, right? It's not. It's negative, oh wait, it was negative, sorry, right? So we're okay. There we go. So there's only 2 here that are kind of new, right? The only two that don't follow what we had in Cal 1 are this one and this one, right? Those are the only two where the signs are off. Everything else is still the same, though. All right, you don't need to memorize those. Just know that they exist and they're on your formula sheet. All right? So where are we right now? We've looked at the new hyperbolic functions, we've defined them, I showed you some properties, and now we've talked about the derivatives of those. We have covered now 12 things, right? 12 functions, 6 in their derivatives. So what's next? The inverses. All right, so we love inverses because inverses undo functions, right? The inverse of a function undoes it. And we love to undo things. All right, so we want the inverse. If I have time, please remind me, I'll put it up here, to talk about a one-way function at the end of class if I have time. A one-way function. All right, inverse hyperbolic trig functions. This is going to be fun. Do you remember in pre-cal, if we said that, so I'm going to get to that, but I want you to just think about this for a second. If we say y is equal to sine of x, then when we tried to define the inverse trig function, arcsine, all we did is we said that arcsine of y would be equal to x. In other words, if you draw it in a picture, if x goes here through the sine function, the inverse function takes that value back. The inverse sine function takes that value y back to x, right? So this is the general property of any inverse. I could do this with e and natural log if I wanted to. But as far as defining it, we didn't have like an algebraic definition of it. I think you ran into this problem in pre-cal. If I give you this, you'll understand what I mean, I hope. If I say arcsine of root 3 over 2, in pre-cal, you're not just going to plug root 3 over 2 into a formula, right? If you did, then a lot of you would have done well in pre-cal and not struggled. Instead, what you had to do is you had to understand that this was asking a question. It was saying, somewhere on the unit circle, my y-coordinate is root 3 over 2. What's that angle? And so you would come up with 60 degrees. It would have been better if to do this computation, it was just like, oh, just take that, square it, add 2, divide by 4. If that were it, everyone would do great, right? But you had to like conceptually understand it, right? Well, with inverse hyperbolic trig functions, I have good news. There's a formula. So you don't have to like reverse think things. It's just a formula. So here it is. The hyperbolic inverse sine of x is equal to natural log, and I'm going to put that little colon here to define it. Natural log of x plus root x squared plus 1, close. There we go.
So what you're saying is that we don't have to memorize how to prove it, we just have to memorize the formula?
What I'm saying is to answer, if somebody asks you to evaluate an inverse hyperbolic trig function, you do not have to have some like weird conceptual visual thing to reference to be able to get the answer. Instead, it's like asking you to plug a number into like a quadratic. You just plug things in, plug and chug. That's nice, right?
Yes.
Okay. Now, here it is though. And then there's the other, on the notes for the class, there's 3, I give you 3 of them. I give you inverse hyperbolic sine, I give you that one. I give you inverse hyperbolic cosine, I give you inverse hyperbolic tangent. The other 3 are in the book, but you're never going to need the other 3, all right? So the first 3 are the only ones that are in your notes. In fact, we will rarely use this one. So there it is. Is it surprising to you that there's a natural log in there? Is that shocking to see a natural log in here? Why not? Because what? Because in the hyperbolic sine function, there's e's, right? E to the whatever. So it makes sense that natural log would be there if it's supposed to undo this, the e's, right? So what we're going to do now is just a really fun exercise. We're actually going to derive that formula. I'm going to show you where it comes from. Like we're going to create that formula. So our goal is to get to this, all right? Now, let's see if you remember something before we do it. College algebra, can you take yourself that far back? Okay, let's say I gave you this nice little linear function in college algebra, and I ask you to find its inverse. Does anyone remember the steps to find the inverse of a function? Okay, so you're going to change the f of x to y, and then you switch the x and y, so you go x here, and you go 3y plus 4, and then what did you do? Solve for y. Okay, that's the technique, all right? So this is the inverse function. And it's pretty cool, because the way it works is like, if I take this function, and let's say I plug the number 1 into it, where is it going to spit that 1 out? What does 1 go to here? Go ahead, plug 1 in. 7, right? Okay, and now if I plug 7 in here, it should go back to 1. So 7 minus 4, 3 over 3 is 1. Yeah, so that's the inverse function. And that cool little way of doing this is the standard process, right? So replace f of x with y, switch the x and y variables, solve for y, we got it. That's exactly what I'm going to do right now. In order to figure out what the inverse hyperbolic sine function is, what I'm going to do is start with the hyperbolic sine function. Okay? I'm going to switch the x and y. And then I'm going to solve for y. Crap, I can't solve for y. Like here it was easy, like move the 4 over, divide by 3. It's algebraic, right? I can't solve for y because the y is inside that function, right? Yeah. So why don't we do this? Why don't we just rewrite what the right-hand side means? Can you tell me what sine hyperbolic of y really is? E to the y. Minus e to the negative y. Now that's looking a little more algebraic. We need to try and get y by itself. All right, I'm going to take a quick break. Like I'm going to walk out, get a drink of water, maybe walk around, do 1 lap around the 3rd floor. And while I'm doing that, I want you to consider how you would solve this for y. I have my suspicion that nobody in here can do it. And that's why I'm showing it to you, because I want to show you the algebra that it takes to do this. It's possible, but not. I've been teaching this for a long time. Nobody has ever come up with a way to solve that all the way through. All right? So let's see if you can. That's why I think it's worth us seeing it. So look, the reason I'm giving you this problem, I wanted you to think about it, is because this is not a very like normal equation that you've ever had to solve. Like, if it was just e to the y, just that right there, you could do this with natural logs. So here's one approach that I've seen. Students will say, hey, let's kill off the fraction. Let's multiply both sides by 2. How about we do that to begin? Is that all right? Okay. So I've seen students at this point say, hey, natural log kills e, right? The natural log kills e. Now don't write this down. I'm writing it in red because it's wrong. If you do this, okay, I want to discuss with you why this move is not going to help. Why doesn't that move help?
Because what's inside isn't just one e.
That's right, because what's in here is two terms separated by subtraction. If you had just that, you're in business, right? But it's the two terms. And there is no way to split this into two things. You can't. The only properties of logs we have were natural log of x times y equals natural log of x plus natural log of y. Natural log of x over y equals natural log of x minus natural log of y. These are properties of logs. So you had multiplication inside, you can split it into two with addition if you have division inside, but we don't have a property that allows you to go anywhere with two things being added. It's not like we never found one, you can't do it. There's nothing, that function cannot be split up. All right, and that's where we are here. So the natural log won't work. So I'm not going to mess your name up. What did you say?
First name is Eugenio, but if you cannot say that, just Gerardo.
Gerardo, that's still hard. Okay, all right. I'm gonna go with, I'm bad with, I can't even remember my own name sometimes. Okay, so look, I like this move of e to the y. And you said that we did that earlier, right?
Yes, sir.
So that's, one of these things, like when you see something happen, always have that like in your arsenal. Like, try it, right? Doesn't hurt to at least try something. So e to the y, multiply on both sides. And so we get e to the y times 2x equals, now when we distribute here, we get e to the 2y minus 1. Now I agree that that is a good first step because it kind of cleared fractions and it got rid of negative exponents. But this is where things get really kind of out there a little bit.
I'm afraid to be wrong. I don't want
Oh, don't be afraid to be wrong. Oh man. Was it Einstein that has, I think Einstein had a quote that said, something like, don't let your troubles in math worry you or bother you. I assure you mine are far greater, or something like that. Like, don't worry about your struggles, like I struggle even more. So look, you have to look at education in what you're doing sitting in this classroom. I always like to try and think about it like way back in the day when someone's trying to show someone like how they figured out how to use a stick to like break something. It's like everyone gathered around and you just demonstrate it and then someone picks up the stick and they like hit someone else with it and they don't know what the hell they're doing. Like, you have to learn by making mistakes, right? Like, everything is about make mistakes, learn, grow from that. I'm bad with stories and analogies, I'm sorry.
couldn't tell.
Okay, so what do you want to do that you think would be wrong?
Oh, couldn't you get rid of the e
How?
when, like, I forgot the name of it, but
The log thing?
yes.
Okay, so we would run into the same problem even with this expression, because here log on this side, we have two things multiplied, so we could split it, and that would be okay. But on this side, we'd have to log here, and we have two things that we can't split. So we'd have the same story on this side that we can't split the log up.
Can we get the e's to the same side?
You could get the e's to the same side.
Or no?
And what?
Is it productive when we do that, to just, group them like we always do?
The e's on one side?
Yeah.
I don't know. Is it productive? Let's find out. Yeah. Okay, so look, I'm gonna choose to do it this way. I just don't like the negative one by itself. I just want it to be positive one. So I move the one over there and I move this over here. I think that's what you wanted me to do. Get the e's on one side. All right. Now what?
And then factor out e.
Then you maybe factor out an e. E to the y, sorry. So I could do that. Look, everything you've done is well within the rules of algebra at this point. Factoring out e to the y, got e to the y minus what? 2x. And then now what? See, at this point you're kind of in trouble. It's kind of like this. And this is going to be a huge hint. Well, I don't know if it's that huge, because this problem is so hard to see anyway. What if I gave you this? What if I said like x squared minus x was equal to 1, right? That's kind of what we have here. It's not exactly, but you would like pull an x out and do x minus 1 equals 1. That's kind of like where we are right now, but you cannot take each of these and set them equal to 1. This only works if this is what? 0, right? Okay, I just gave you a pretty big hint though. Let's go back one step. Let's go back 2 steps. Instead of bringing just the e's to one side, let's bring everything to one side. And I'm going to do it this way. I'm going to move these over to this side. And watch the order in which I put these. Do you agree with that? Okay, now you have to really kind of break down some of the walls that hold you in here. Do you remember this thing? The good old quadratic formula? The good old quadratic, right? Quadratic equation. We can always find the solutions to this using the quadratic formula. It says, the quadratic formula says that the solutions to any quadratic equation are x must equal negative b plus